So, as explained before, without any aberration correction through the skull, because of the defocusing effect of the skull, it is impossible to achieve an accurate focusing through the skull. Nevertheless, by using arrays of transducer and by shaping the field in order to compensate the aberrations induced by the skull, it is possible to restore a good focusing through the skull, for example, either to do some ablation in the brain or achieve neuromodulation. But those systems are quite expensive. And a third option is actually to use a single element, but try to generate the same wavefront that is shaped to compensate for the aberration of the skull. Like that, it would not be possible. Physically, this is just impossible. But by adding an acoustic lens in front of the transducer, which thickness is calculated exactly to create the wavefront that is going to compensate for the aberration of the skull, then it is possible to do so. So we showed that it was actually possible to build such a lens, and in that case to achieve a millimetric precision through the skull. And you see here again, without aberration correction, you see a split focus, but by using the lens with the appropriate thickness in order to compensate the aberration for the skull, it is possible to restore a good focusing through the skull. And this is on average on 3 different skulls. You see that we are able actually to generate 10 times more energy at the focal point with the corrected beam compared to the non-corrected one. So what would be the potential impact of the lens on transcranial ultrasound stimulation? Again, looking at past work that has been done in humans in the past. This is an example of a study. Again, this is a retrospective study where we estimate the pressure field inside the brain. On those patients, you see a shift between the intended focus in red and the actual refocusing in blue. This is without any acoustic lens. With the lens in place, you see that this time it is possible to restore the focusing and be able to modulate brain activity at the right location. Another example here with Brinker et al., where you see quite a significant shift between the target and the actual focus. And with the lens here, you see there is a slight shift, but again, at least the area that is stimulated is within the same areas than the one that was intended to be targeted with ultrasound. So such a lens is able to compensate for the aberration for this specific point. Make sure that it's possible to focus on those areas. But in some cases, you know, at the last minute you might want to change and sonicate in a different area. So how does it work? In that case with a lens, because the lens is casted for one given location. Actually, it is possible to steer the beam by using such a lens. If we move the lens and the transducer at the same time, it's going to compensate the aberration of the skull as well. This is based on what is called in optics the isoplanatic angle. In optics, what astronomers do when they wish to compensate the aberration induced by the atmosphere when looking at the stars is that let's assume that they have a target, a very small star that they can hardly see in the sky. They look at a reference star, a bright one, a very bright one, but they don't see a single point. They see the star with some halo around because of the turbulence of the atmosphere. So what they do is that they shape the telescope. You know, nowadays telescopes are made of thousands of telescopes, little ones, where they adjust the position of each in order to compensate for the aberration of the atmosphere and be able to restore a bright star with a bright spot. And when they do so, then they look around and suddenly they see this tiny star that they could hardly see before, and they see it very bright because now the atmosphere has been compensated for. It's the same for us. This is the target for more simulation. This is where we would like to refocus with the lens. So we cast the lens for this location. But let's assume that we steer both. You see that here the lens is calculated to compensate for the effect of the skull here. But when you steer the beam, it's almost the same part of the skull that is affecting the beam, except for here the edges in here. So it means that we should still be able to refocus the beam here in this location. So let's check. We did the experiment here. We refocus the beam here at the central location. We cast the lens, and we see that this is the aberrated pressure with different skulls. And you see that we don't have a very good refocusing as compared to the refocusing that we obtain with the lens. And then we steer the beam. We steer the beam, again, the beam is still defocused, but it stays focused by using the lens. And we go further away and away and away, and you see that we can still keep good focusing. So basically up to 1 centimeter away, we can use the same lens in order to compensate for the effects. We did the same now in the elevation, so we can also change the depths of the focusing, and again you see that the refocusing stays correct here as we steer the beam away, and again 1 centimeter. So it means that it is possible to not only compensate for the aberration from one target, but once you have the lens operates also very well by compensating the phase aberrations, let's say in a 1 centimeter box around focus, actually 2 centimeter, 1 centimeter in each direction. So of course, there's a growing interest in using such lenses with either numerical studies or studies with 3D printed skulls, or here experiments on human skulls. And there's a lot going on currently by using the lenses. I know this study here is most well known, but this one, the steering capabilities, is actually more important in terms of translation to the clinics in order to be able to use those lenses in the best way possible. So stay tuned. For example, the Sonomine project is currently aimed at developing a neuronavigated lens-based aberration correction for adaptive and for precise deep brain stimulation. So soon we will be able to target deep areas in the brain for neurostimulation by using either multi-element arrays with the Insightec machine or lens-based correction. Last, what about the mechanisms of ultrasonic neuromodulation? There's been lots of possible explanations, and I'm going to review some of them. The first one is a very nice model, actually, that is explaining neuromodulation in terms of intermembrane cavitation. And what they do is that what they say is that there are some nano bubbles trapped into the lipid layer of the membranes. And those bubbles, if you have a look to Larry Crumb's presentation, MOOC course number 7, look at, he described old cavitation. So it will help you a lot understand this model. Basically, what they do here is that they hypothesized that there are nanobubbles trapped here in the bilayer lipid membranes, and that those nanobubbles are going to grow by rectified growth each time ultrasound pulse is making these bubbles oscillate, and that they will grow until they become microbubbles, and they can actually here separate those bilayers and trigger action potentials. So it's a nice model. I liked it a lot for many years. And but the thing is, listen to Larry Crumb's presentation and then do the math, and you see that in order to grow nanobubbles with megahertz ultrasound is difficult, because we are way out of the resonance frequency of the bubbles. But it might explain why it takes time to induce neuromodulation when we use pulsed ultrasound. Usually just one pulse is not enough to induce ultrasound. We need several pulses, and they were able to explain lots of the experiments that have been conducted in the past. Another mechanism is the involvement actually of mechanically sensitive voltage-gated channels. And this is a very nice paper actually from the Tyler group, where they showed with calcium imaging that when they were sending ultrasound, they could see the calcium channel opened. So clearly, voltage-dependent calcium channels are at stake, and as well as mechanically sensitive voltage channels. So that's for sure. Mechanical effects are very important in explaining the mechanic or the mechanism of neurostimulation. And actually, there's another way to understand neurostimulation. This is the one I have to admit that I prefer, which is the flexoelectric effect. If you look at the size of a neuron, and especially the size of a neuron in humans, they are quite elongated, quite long. You see typically 1 millimeter. So it means that when we emit ultrasound, we're going to bend those neurons. And when we bend those neurons, actually it can depolarize the membrane and trigger action potentials. And I encourage you to go and have a look at this paper from Antoine Jerusalem group, where they showed that when you bend a neuron like that, you can trigger action potential, and depending on the energy deposition, you may predict when action potential are going to be triggered. And the fact that we move tissues, we know for sure with acoustic radiation force. Of course, we move tissues, and we can even quantify with the type of pulse that we use during neuromodulation. Charles Kasky's group in the US and Vanderbilt University here showed very nice images with MRI. You see here using MRRF techniques, so acoustic radiation force imaging techniques. You see clearly a displacement around 1 micron here within tissues, with actually ultrasound parameters that correspond to what is currently used in neuromodulation. So typically we induce a 1 micrometric displacement which could induce actually action potential within the brain. We confirm those results here in our group again with the same parameters as we used for neurostimulation, slightly higher to be able to clearly see the displacement. Again, you see a micrometric displacement, so similar in both studies. And actually, we were able to do simultaneous measurement of not only the displacement, but also the temperature. So there is some thermal rise here. It is small, 0.6 degrees, but there can be some thermal rise. So which leads me to the last effect, potential impact of thermal rise. And let's have a look to some recent studies here that have been performed on rats. You see, depending on the studies, they used different frequencies. So Kamimura was at 1.9 megahertz here. This is a study from Yunnan et al. In our group with a lower frequency. So you see that with a higher frequency, it is much more precise here, but we are not only able to simulate the acoustic pressure, we can also simulate the thermal rise. And depending on the parameters here used in those different studies, you see that they used very different parameters. I mean, the maximum pressure in the brain is varying within the similar ranges, but it can at least double depending from one study to the other. Sonication time also can change quite significantly from one study to the other. And all combined together, most of the time for neurostimulation, the thermal rise would be negligible. If you look at the simulations here, you see that the thermal rise is less than 0.01 degrees, except for one study here where the thermal rise was actually almost 2 2 degrees, and the maximum temperature here within the brain was actually 44 degrees. So it means that the thermal rise was almost 7 degrees. And this was confirmed here by thermocouple experiments. And you see here, if we used, I would say, the Kamimura type sonications, the thermal rise is quite significant. And for others, you see that the thermal rise is quite small. So depending on the sets of parameters, thermal rise can be completely ruled out. And so I strongly believe that the mechanism for neurostimulation is a mechanical one, mechanically sensitive channels or bending of the neurons, but clearly some micrometric, in both cases, I mean, both are also compatible. Both could happen. But I really think that the micrometric displacement of the tissues is responsible for neuromodulation. Some studies might also take advantage of thermal rise, but that's a different phenomena that can be ruled out for most of the current neurostimulation studies. I would say for almost all the studies that I presented today, except for this one, the thermal rise was less than a degree, way below a degree. So I would say that transcranial ultrasound stimulation is just the beginning of a field that is currently translated into the clinics. We did a long way. I mean, when I say we, it's our group together with many others that I cited in this presentation. So ranging from rats, mice, to monkeys, and to humans, and now pretty soon, so as I told you, systems will be available either within DMR or neuronavigated, and I see a bright future in neurostimulation. Thank you for your attention. And if you wish, you might send me any question at the following email. Thank you very much.